Hi, this is Rick Kolk, and today I'm going to discuss VisSim Embedded Modeling Fundamental Concepts Part 3. This video will cover the following topics: controlling the read and write order of execution in the VisSim Codegen, creating vectors using the VisSim buffer block, and configuring the plot block to display vectors. Specifically, we'll discuss the external trigger, setting the x-axis range, and setting the x-axis label. The VisSim execute order block, located under Blocks Signal Consumer, causes inputs to be read and used in a predefined order. In this example, we're reading in 6 inputs, a combination of hardware and software points, and assigning them to variables V1, 2 through V6. Before they're being used in the summation, we are using the execute order block to configure the order in which the inputs are read into this model. In this example, V6, 5, and 4 are read in first, followed by V1, 2, and 3. If I go to Tools, Codegen, Generate Code, and View the Code, I can see the effect of this execute order block in the code here. You'll notice that V6 is used first, followed by V5, V4, V1, V2, and V3. The order that I have specified in the XE order block. Now let me change this block, and what I'll do is I will rewire the 1, 2, and 3 to the first input, and I'll wire V6 to the last input. Re-execute code, Codegen, and view it, and now look at the order in which the inputs are being read and used, and I see they're being used as V1, 2, 3, 5, 4, 6, the order that I've specified. Similarly, it is sometimes necessary to control the order that outputs are written to the VisSim Codegen. VisSim uses vertical placement of blocks or enable compound blocks to define the write sequence. Blocks at the top of a model are written before blocks at the bottom of a model. Let's illustrate this with the Codegen. On this model, I have an output extern float OAT EST, followed by 2 additional outputs, FPF1 and 2. Let me generate code and view the Codegen, and you'll see that I have an output OAT EST that occurs prior to FPF1 being set to 0, which occurs prior to FPF2 being set to 0. Let me change the order. I'll simply move this extern OAT EST down below the FPF1 and FPF2 writes, regenerate code, view the code, and scroll down, and we can see that FPF1 is written first, followed by FPF2, and last by OAT EST, being located at the bottom. Frequently, it's necessary to store a sequence of signal data for matrix processing or plotting. The buffer block serves this purpose. Located under Blocks, Matrix Operation, the block accepts a scalar input, shown by the narrow line, and produces a vector output. Properties are shown in this window. The buffer length, which is the number of elements in the buffer, dt is the time spacing between elements, and 4 checkboxes: add input trigger, add buffer full output pin, use circular buffer, and reverse buffer. The first 2 checkboxes are self-explanatory. We'll focus on the circular buffer and reverse buffer in the next example. This example illustrates the use of the buffer block configured 4 different ways, involving the circular buffer and the reverse buffer. Each buffer is configured to run 5 elements at the time step interval that I'm using for the simulation. I'll single step, feeding my ramp in. Initially, what you'll see with no check marks is the buffer will begin filling from the left-hand side, and as I increment in single step, it continues to be filled from the left-hand side until the buffer is full, and then it simply moves the window to the right, and we lose the oldest element. In the second example, with the reverse buffer on, what we see is I'm filling from the right. As I single step, I add new elements in at the far right, and I begin losing elements off the left side of the buffer. Now turning the circular buffer on and reverse buffer off, repeating the same example, I initially single step and I fill in the rightmost element, single step again and fill in the adjacent element to the left, and as I continue I fill elements leftward until I fill the buffer. Then I begin writing over from the far right and leftward. And finally, circular buffer on, reverse buffer on. Single stepping through this, I begin filling the buffer from the left. As I single step, you'll notice the buffer is filling rightward, and then I continue to circulate back and write new elements in from the left to the right. The plot block can be used to display vector data from a buffer block by selecting the external trigger checkbox located on the plot options properties. When the external trigger checkbox is selected, a small green round input pin will appear on the upper left corner of the plot blocks. Anytime that this pin is pulsed with an input, the plot will display the contents of a vector fed into any of its input pins versus the vector's sample number. Normally, when the plot block is used to display vector data, 4 steps are applied. First, the external trigger is selected. Second, instead of displaying sample number, the X upper bound and lower bound are defined to fit the data. Third, fixed bounds is selected in the options menu. And last, a meaningful label is given to the X-axis. To illustrate how the buffer and plot blocks are used together, we will capture a time history of 100 elements of a sine wave in a buffer block and then plot them in an externally triggered plot block. The sine wave frequency is 2 pi, which is equal to 1 cycle per second. The simulation is configured with a time step of 0.01 seconds and an end time of 100 seconds. Setting the buffer length to 100 and the time step dt equal to 0.01, which equals the simulation time step, the buffer will then capture 1 cycle of the sinusoid. We will configure the buffer with the buffer full output pin checked, circular buffer checked, and reverse buffer checked. Based on this selection, the buffer block has 2 output pins. The upper pin is the buffer full output and the lower pin is the buffer data vector. The buffer full output pin outputs a pulse when the buffer is full. Since circular buffer and reverse buffer were both checked, the buffer block will fill from left to right. Once the buffer is full, 2 things happen. The buffer full output pulse will go high, or 1, and the buffer will automatically begin overwriting its elements from left to right. When the buffer block is connected with other blocks, the buffer full pin is used to indicate to those blocks when the buffer data is ready. The plot block will be configured with the external trigger on, the axes set to 0 to 1 in seconds, fixed bounds on, and the X label will be time in seconds. Running the simulation, we see a plot of 1 cycle of the sine wave. A plot block configured with external triggers selected will display an n-element buffer with sample 0 displaying its leftmost element and sample n-1 displaying its rightmost element. If the buffer block in this example were modified by unchecking the reverse buffer, the buffer would fill from right to left instead of left to right. Since the buffer block is recording exactly 1 cycle of the sine wave, a plot of this data will display a sine wave that will appear to be phase shifted by 180 degrees, which is the same as multiplying it by -1. To illustrate this, the reverse buffer checkbox in the buffer block is deselected. Running the simulation reveals the effect of this change.